Mhm. So as I was telling that in this problem, yes, so I had a mock test to give, so I couldn't. Okay, no worries, no problem, no problem. Okay, so as I was telling Marita that you could have written the force, the acceleration like F by m1. If you had different masses, then you could have used this equation also. Any way you like. You could use the work energy problem, work energy theorem, or this in place of acceleration, you could have written F by m1 and then compare these two planks, right? So if you see the say third equation of motion, what do we have? So we have hmm, we have what? Yes. So we have v square minus u square is 2as, right? And if we take 2 in this side, so this becomes what? Half v square minus u square. So this is third equation of motion, right? And this becomes what? As, right? So we multiply m in all the sides. So this becomes half mv square minus half mu square, and this becomes mas, right? So this is force. So this is work done, and this is what? K final and K initial. So this is the work energy theorem, right? So yes, Marita, you were correct. I apologize for this mistake, right? So we finished up to this work energy theorem, right? And the next part, so we did the kinetic energy, right? Now the other part of mechanical energy was the potential energy, right? So I will not discuss about the definitions because we don't have the time. You already guys know the definition of what is the potential energy. It arises due to the conservative nature of forces, right? So before I talk about the conservative nature of forces, let's talk about what type of force do we have. So there are two type of forces. One is the conservative force, right? And what is a conservative force? So it does not
Depend on path.
yes. So it does not depend on path. Yeah, and the second thing is that the loop integral is zero. So work done in the loop is zero, right? So this shows that whatever, so these are 2 points, and if the force is conservative, so whatever path you choose, you come from here. The work done will be the same, right? And if you complete one loop, then then your, I'm sorry, let one moment, guys, please. Sorry about that, guys. Okay, so where was I? Yes, so conservative force, and what are the example of conservative force? Yes, so conservative force are gravitational forces that we talked about yesterday. Gravitational forces and then electrostatic forces. And then you have spring forces, restoring force in the spring, right? So, and what are the non-conservative force? So this doesn't depend on path. This depends on path. So it depends on path. Right. So these are the example of, and what are the example of non-conservative force? Dissipative forces, right? So what? Dissipative forces. Just for example, the what? The frictional forces. Frictional forces, or just like you some damped forces, right? So these are the non-conservative forces, right? And let me give you an example of the conservative force for, so we have what? Potential energy, right? So there are two kinds of, not mainly, but mainly there are two kinds of energy. One is the gravitational potential energy that I will talk about here. I will not talk about the electrostatic energy that you guys have done in your what? In your 12th part. Amna ma'am have done that electrostatic part. So, and the other one is the spring, which is the restoring energy. Restoring energy. Right. I need to rush because I have to complete. Right. So this is due to the gravitational force, and this is due to the restoring force, right? So this potential energy arises due to this work done against or in the direction of this gravitational force, or the work done with respect to this restoring force is called the spring or restoring energy, right? Okay, so let's give you one example. Let's say you have a particle which goes from here to here, right? Straight, right? So what is the work done in moving this object to this much, right? And let's say you have another type of same height. So you have, this is some height, and then you take this mass up to this point, right? But in this path, you follow this path, right? But the same height. And let's say again you follow the stairs type of path, right? Okay, so this much. So this is, let's say, H1, this is S1, this is H2, this is S2, and this is H3, this is S3, and this is H4, and this is S4, right? So this is, the work is done against the gravitational force, right? So we'll have the gravitational potential energy. And as the force is conservative in nature, so the goal is that the work done should be what? Work done should be same, right? Whatever path we have chosen, this path, or this path, right? This path, right? So the work done should be the same, right? So let's just calculate the work done. So what would be the work done here? So work done would be Fs cos theta, right? Let me draw it like this. So then this is right. So what is the force acting on this object?
Weight.
Yes, so the gravitational force, right? And the displacement is in this direction, right? So the angle is what? 180 degree, right? So the angle is 180 degree, your force is weight, right? And displacement is h, and angle is 180 degrees, so minus. So the work done is minus mg, right? And let's calculate the work done for this case. So for this case, we have this guy here, this is theta, this is theta, right? And what? So this is mg cos theta, this is mg sine theta, right? So what is the force here? Force here is mg sine theta, right? And what is the height here? What is the length that it completes? So let's say this is L, right? And let's say this is B and this is H, right? And this is the displacement, right? So what is the angle between the force and the displacement? Theta prime is what? 180 degree. Am I correct, guys?
Yes, sir.
So
Yes,
F,
sir.
sorry, Nimra. Okay. Hello. Yes, so force is what? Mg sine theta. And the angle between and the displacement is what? Let's say S is what? L. And theta prime is what? 180 degree, right? So your work done in this case will be what? F prime S cos theta prime, right? So this is mg sine theta. And our guess is that it should come like this, right? Because it doesn't depend on path, right, guys?
Yes, sir.
So this is our aim, right? So this is mg sine theta, and okay. Yes. So this is mg sine theta, this is L, and this is minus, right? So this is minus mg sine theta L. And we have to take care of this guy and this guy somehow, right? Because this should give H, right? So let's take this triangle. In this triangle, we have this theta, this is B, this is H, this is L. And we have sine theta here. So what will be sine theta? Sine theta will be P by H, right? So L. So this will become H by L into L. So this is minus mg, right? Because this should be the answer, right? So we have seen that both the path gives the exact work done, right? Again, in this problem, so up to this point, as we have calculated, so up to this point, we will have what? For this stair problem, sorry. Yes. So for this stair problem, what we will have? We will have work done. So work done will be for this part only. This will be minus mgh1. And for this case, the displacement is here, right? And the force is here. Force is where? Force is, we are what? So the displacement is here and weight is here, right? Right, guys? So the angle is what? Angle is what? Between the displacement and this force. We are working against the gravitational force. So the angle is 90 degree, right? So this will be 0, right? And for this case, we will have mg H2 plus 0 minus mg H3 plus something like that. So this will give mg H1 plus H2 plus H4. Right, so this will become minus mg. Right, so you see that the work done doesn't depend on the part for the conservative forces, because only the force that was working here was the gravitational force. Right. Okay, so this was about the conservative and the non-conservative force. The second thing is that the equilibrium, right? So let me, before I do equilibrium, let me do one more. Okay, so let's complete equilibrium. Okay. Hmm. Yes. So there are three kinds of equilibrium, right? As I told you in the previous class. I'm sorry, guys. I am going very fast. I don't know what to do because we have to finish the syllabus very quickly. Right. So yes, there are three kinds of equilibrium. One is the stable equilibrium. Right. The other one is the unstable or unstable. What do you say? Unstable equilibrium. And the third one is the neutral equilibrium. Right. So whenever this type of question asked, so in this type of question, they will give the form of some U, potential, right? And by looking into the potential, so let's say this is some K by R square plus B by R cube, something like that. K by, as you guys have already learned. So in your nuclear force, you have learned about this kind of potential, right? So this goes like 1 over R square plus 1 by R, something like that, A by B, this kind of potential. Right, so you will be given some kind of potential, right? Let's say C by R4, and they will ask you whether this is in or unstable or constant equilibrium. So just picturize this to understand the stable, unstable, or the neutral equilibrium. Just picturize. Say you have a bead, right? And the bead is in here, right? And let's say this is one bead which is here, right? And the other part is, let's say you have this bead here, right? So if you move this bead here, right, what will happen? It will go here, and then what will happen?
It will return to its original
Yes,
place.
right. So it will come back to its, it will then come here, then come here, and then from after some time, it will retain its original position, right? So if the particle or if the bead retains its original position, then it is called the stable equilibrium, right? So this is stable equilibrium. And if you move this particle or this bead in here, so this will fall down, right? So that is why this will be called the unstable equilibrium, right? And this is the neutral problem. So if you put this guy here, so it will not come, but this will be in the neutral equilibrium, right? So your potential energy is constant, right? So mathematically, how do we solve this problem? So this is the what the representative part, and the mathematically, what do you mean by the stable equilibrium? So you see that this is the case of minima. So if you have greater than 0, so this will represent the stable equilibrium, right? So if you have given some form of UR, right? And so you have to calculate first, and this case is represented by, right? And this is 0, right? Not d square, but so d square du by dr, right? So these are the cases of the stable, unstable, and the neutral equilibrium, right? So let's say you are given some, let's say 3 by r square plus 2 by r4, right? So when they ask you about the equilibrium part of this question, so what you do is that first calculate the critical points, right? I don't know what will be the graph of, so what is the graph of 1 over r square? So 1 over r square goes like this, right? And 1 over r4, so let me take a minus sign here. So let me take a minus sign. So minus of 1 over. So this will be a steep kind of, right? So this is minus of 1 over r4, and this is 1 over r square, right? So when you combine this, then you will have an effective diagram will be like this. So this will be like, right? So this will be your effective diagram. So you see that you have how many equilibrium points? Arpit, can you guess from this diagram? From this diagram, how many equilibrium points? Arpit, am I audible to you? Marita, can you tell me by looking into this graph that how many equilibrium points will be there?
So 2.
Right, 2. So this one, the neutral one, and this one, the stable one, right? If you put a particle in here, and this will roll down, come here, so this will be the stable part, and if it comes here, then so there are 2 equilibrium, right? So first, when we are given this potential form, this potential energy, so what we do is that we calculate the first derivative. We calculate the first derivative, which is du by dr, and then we put it to 0. So when we put it to 0, this will give the critical points, right? So let's say this is the UR, and you take first derivative of this UR. So this will become what? 3 minus 2 and R cube, right? And this is plus how much? So 8 and R5, right? So this is 0. So we have what? Minus of 6 by R cube plus 8 by R5 is equals to 0. So we take 3 by R square R cube common. So we have what? 1 minus 2 by R minus 2 and plus of what? So we can take 3 common here, right? So let's take 2 common. So this is 3 and this is 4 by what? R square. Right. So this is 0. So whatever the value of R we get, those are the critical points. Right. So we have this part is 0. So we should not bother about this. So 4 by R square is what? 3. So your R square is 4 by 3. So R is 4 by 3. How many values do we get? Samaira, Namira, how many values do we get? Anna. Oh, Iram has joined. So Iram, how many points, how many critical points do we get from this part? Abhinav. Yes, yes, 2, right. Plus minus 4 by 3. Right.
Yes, sir.
So we have 2 critical points, and now we will calculate the second derivative. So we will calculate the second derivative. Second part, calculate the second derivative. Right, so this is du square u by dr square. And then whatever this value comes, let's say this function of r, we will find those values at these critical points. Right. So if this value is greater than 0, then we will have what? Stable equilibrium. I'm just telling you guys because I have to cover a lot today, right? So you guys calculate and see whatever the value of this second derivative comes, and if at the critical points it is greater than 0, so that will be stable equilibrium. And if this is less than 0, so that would be unstable equilibrium. Right, guys? Okay.
Yes, sir.
Okay, so now one more thing that we have to know before I go further, that your force and potential energy are related, right? So your force, if you have a conservative force, this is related by dV by dt, right? So whenever you have some potential energy given, you can calculate the force from, right? Okay, so yes, so next topic is this conservation of mechanical energy, right? And so you guys have already heard so many times about this uh, conservation of mechanical energy. Right. So what does it say? That if you have conservative forces are involved, right? So the total energy So your total energy will be conserved. Right, total mechanical energy. Conserved. Right. If conservative forces are involved. Right. So you let's say you have the initial energy like this. So you have potential energy initial, total energy initial is equals to total energy final. Right. So total energy initial is what? Potential energy plus kinetic energy. And what is the final energy? It is potential energy final plus the kinetic energy final. Right. So if you take all these here, so this will be what? Kinetic energy final minus kinetic energy initial is what? Kinetic energy final. So this goes here, this comes here. So this is PE initial minus PE final. Right. So, and what is this, guys? Tanya, what is this?
Work done.
Yes. So from work energy theorem, we know that this is work done. Right. And this we can write as P final minus P initial. Right. So work done will be the negative of the potential energy. Right. Okay. So work done is what? Delta K. Right. And this is also equals to minus of delta. Right. And so what I was going to tell that if you have conservative force, then your work, so this is delta K minus delta U. So this is delta K plus delta U is 0 for conservative forces, right? And let's say if we have some non-conservative forces, then this for non-conservative force, we will have delta K plus delta U will be work done by dissipative force. Dissipative, I don't know. Right. So this will not be equal to 0. Okay, any doubt up to this point? Guys, yes or no, or
No doubt, sir.
okay.
Yes, sir.
Okay, so let's do some question based on this. Okay, I forgot about the potential energy due to spring force, right? So, okay, so this problem, before I do this, let's calculate the potential energy due to restoring force. Okay. Yes, so yes. So in this part, I calculated work done to be minus mgh. Right, I calculated work done to be minus mgh if we were going, if we were working against the gravitational potential, right, gravitational force. Right, so work done was minus mgh. So then what would be the potential energy? It's actually delta U, but this,
MGH.
right. So this will be minus of work done. So this will be mg. Right. Okay, so what I was saying. Yes, so sorry, what happened? Mm, yes. See, so other conservative force was what? So the other force, conservative force, was spring force, and which is what? Restoring force. So this is equal to what? So if you have a spring, right, and if you pull this mass over here, so you apply some force, and if you pull this object here, right? So this is spring will work this motion, right? And this will try to get back. So that force is called the restoring force, right? So that force is called the restoring force, and this is equal to how much? By Hooke's law, you already know that this is minus px, right?
Px.
Right. And if you solve this, so if this is MA, right, and this is minus of kx, so this is mx double dot plus kx, right, equals to 0. And this is x double dot plus k by mx is equals to 0. So this is equals to 0, and this follows a simple harmonic motion. This you guys have already learned, right? Where your omega square
Yes,
is the
sir.
angular frequency, right? So what I wanted to talk about here is that the work done for this case. So let's say that you displaces this object up to here, and the displacement is, let's say, x, right? So what will be the work done? This will be f dx, right? And this is 0 to x, and your f is how much? Minus kx dx, 0 to x, right? So this becomes minus k and x square, x to 0. Right? So this is minus of half and k x square minus 0 square. So this is, so work done will be how much? Right. Okay. Yes, so work done will be how much? Minus of half kx square, right? So what will be the potential energy for this spring system? For this spring, half kx square, right? Right, guys? Okay, so this was about the potential energy of this spring. So up to this point, we have learned what? we have learned the work done by some forces, right? And then we saw what is the kinetic energy of a system. And then with this work done, and then yes, so yes, okay. So yes, so and then we talked about the potential energy, right? So we saw the for the two case of conservative forces, the gravitational forces and the spring forces. We calculated the potential energy, right? And then we learned about the what equilibrium, three kinds of equilibrium: the stable, unstable, and the neutral equilibrium. And then we also learned about this what this conservation of mechanical energy in case of the conservative force and in case of the non-conservative force. I am not doing problems here because I have what uh, half an hour left, and I want to complete the collision and the elastic and the inelastic collision, right? So, okay. So let me see, can I do some question? Okay, so let's do this problem and then we will talk about the collision, right? Hmm. Let's do it here. Right. So, okay, so this is the problem that an object slides down from here, right? It starts to slide and then stop at some point, right? Right. So this surface has some friction. So this slider doesn't have this height doesn't have some so there's some friction, right? So this guy slides from here, starts to slide from here, and then stops at some point. Let's say here, right? Let's say here. So we have to calculate where does it stop, right? So up to this point, whatever concept that we have learned so far, which concept we will use to solve this problem, right? So whenever you see the velocities are involved, right? Velocities are involved. So you have to just quickly remember, guys, that whenever velocities are involved, so there will be some kinetic energy, right? So, and whenever there is some kinetic energy, we can apply what? We can apply what, Arpit?
Conservation. Oh,
Conservation. So I have to check whether because this time I will not say that if that applies or not. Yes, so we can apply the conservation. You try it with the conservation, but yes, we can apply the work energy theorem, right? So you can check, Marita, that yes, so But for the, yes, so for the conservation of mechanical energy, right? You have what here? This is which force? For the horizontal part, Marita, you have which force?
Sir, the friction.
Yes, so non-conservative force, right?
Okay, okay.
So
Yes,
yes,
sir.
so for non-conservative force, we have to apply this part. Yes, so it can be solved from this, but we have to apply work done by frictional forces, right?
Yes, sir.
Because this time I will not say no that we can't solve. Whatever method you choose, whatever you feel that it can connect to this problem, whatever application we can use, so that will solve our problem, right? So what I was telling that we see that the velocities are involved. So in here, the velocities, there is some velocity, right? And in here, the velocity is 0, right? So we can apply the work energy theorem, right? So what is the work energy theorem? That W total will be KF and KI, right? Right, so W total will be what? Work of gravity plus work of friction, right? And K final is 0, right? And this is half mv square. Am I correct, guys?
Yes, sir.
Now, what will be the work done because of gravity? Fs cos theta, right? Work done due to gravity, let's say Fg cos theta, right?
Yes, sir.
So the force is downwards, right? And the displacement is also downwards. So the theta is 0 here, right? So this is mg and this is how much? H.
MGH.
So this work is mgh, right? You can see that you can see that you are going in the direction of you are not working against the gravitational force. You are working in the direction of the gravitational force. That's why your work is positive, right? And for the case of this guy, so this is moving like this and this guy is stopping like here, right? So friction forces is acting like this, right? And this is the normal, right, which is equals to mg. So the work done due to friction will be what? Cos theta is 180 degree, right? F is F, right? And let's say this is how much? Let's say we have to find from where it stops. So let's say this is x, right? So your displacement is x. Am I correct, guys? Arpit, Marita, Sanya, everyone. Am I correct?
Yes,
Yes, sir.
Okay, so this will be what? Theta is 180, so this will be minus, and F is what? Mu K N, right? And S is X, so this is it, right? So this is half of mv square, right? Right, guys?
Yes, sir.
So let's say your G is 10 meter per second, right? And so this, uh, so this is how much? mgh, h is 1.5 meter, mass is how much? Okay, so I didn't write the mass. So mgh minus mu k mgx is equals to minus half of mv square. Right, so m gets cancelled. Right, so this will become g is 10 into 1.5, and this is mu k is what, 0.2, and g is 10, and x we have to calculate, and what we have half of v square, right? So this is how much? So this is 15, right? This is 15, and this is 0.2 into 10, so this is 2x. And this is minus of half v square, right? Right, guys?
Yes, sir.
Okay, and we have to find the velocity here, right? Because then we will be able to calculate this x here, right? So how will we calculate? Okay, let's say that this guy comes here and then it goes here, right? Right. So this again. Okay. So how will we solve this problem? Did I miss anything? Uh, can we use another thing? Oh, okay, so there are no information about the velocity, right? So this will come in the form of velocity, right? So let's say there some initial velocity was given. Because we can't calculate this problem without the velocity, right? So let's say that some initial velocity v, which was, let's say, 3 meter per second, right? So this was given. I would have missed that part, right? So let's say the velocity is given, so your x will be what? So this is 15 minus 2x, and this is minus of half, and this is 3 square, right? So this will become what? 15 minus 2x, and this is minus 9 by 2. So this guy comes here. So this is minus 9 by 2 minus 15. So this is how much? 2x and minus 9, and this is 30 by 2. Right. So this is 2x and this is minus 39 by 2. So x is 39 by 2. Right. So this is how much? So your x is how much? 9 point something, right? 9 point what? 75 meters, right? So your x is what? 9.75 meter, right? You can see from here that that this length is only how much? 3 meters, right? So what can you tell, Arpit? We have found out that this will stop at x is 9.35 meter. 35 or what? Did I calculate it correct? So 7.5, right? 7.5. So 9.75. So what does it tell about this? What does this distance tells? Marita, can you guess? Marita, am I audible to everyone?
Yes, sir.
Yes. So physically, what does it signify? This
Sir,
X.
it is.
Yes. Yes.
It does not follow this path anymore. It has moved away from this path.
Yes.
If not, it would be oscillating in this.
Right. So right. That this is 1.5 meter, right? And this is 3 meters, and your X came out to be 9.75 meter. So your initial velocity that you gave was so high, and your kinetic energy was so high that this kinetic friction will not be able to stop it in here, right? So the body or the object will come here and it will come here and then it will then drop down, right? So am I making any sense? Because this is 3 meters, right? And it has crossed this 3 meter and then 1.5 meter, and then it went right? Any sense? Ah, Marita.
Yes, sir.
Yes. So yes, so we have provided. I just assume the velocity, the initial velocity to be 3 meter per second. So which was very high, right? So in the question, you will find somewhat lesser initial velocity, and that will stop this object somewhere here, right? But with this initial velocity, your kinetic energy is so high that it will not stop. This friction will not be able to stop it here, and this will go beyond this bowl or whatever this is structured, right? So this was the point that I wanted to tell. And what we have half an hour, so let's do collision, right? Because we will not have time to. Yes. Yes. So collision, as your minds are colliding with the concepts that I am talking about, and if so, there can be two scenarios, right? That whatever I am telling, and then it goes into your mind and then reflects back, or it deviates, right? So either it may be an elastic collision, that whatever I say, it goes beyond, right? And if you guys are able to capture them, then that collision is right, right? Okay, so two kinds of collision. Let's say, you have one guy here which has mass m1 and which is moving with some velocity u1, and some another object guy which is moving in the same direction, right? So the and it has some velocity u2, initial velocity, and this guy comes here and they collide. Right. So with u1 velocity, and this was moving with u2 velocity, m1 and m2. So Sanya, tell me what will be the relation between these two and these guys are moving in the same direction. So what should be the relation between these two that they should collide? Can you tell me? Anna, Idam, can you guys tell me what would be the relation between these two, U1 and U2, so that these guys collide with each other? Right. Let's say if I'm chasing a guy and my speed is, let's say, U1, and then the other guy who I'm chasing is moving with some another velocity U2. So what should be the case that I will be able to chase that guy down? So what should be the relation between my velocity and that guy that I am chasing? Any guesses? Viram, Anna,
U1
Arpit?
is greater than U2.
Yes, yes, yes. So that's when I will be able to chase that guy, right? I will be able to catch that guy, right? So correct. So when these guys are colliding means that U1 is greater than U. Right, absolutely right. And then it collides, and then this guy, the M1 guy, moves with velocity V1, and this other guy moves with velocity V2. Right. So one thing that decides what kind of collision. So there are two kinds of collision. So one collision is what? Elastic, and the other collision is inelastic. Right. So what factor decides the elasticity of the collision? So there is a factor which is called the coefficients of coefficient of restitution. Right. So this guy epsilon, this guy decides whether the collision is elastic or inelastic. Right. So if your value is 1, then the collision is elastic, and this value is 0. So this is elastic but perfectly inelastic, but perfectly inelastic. Right. And what is the value of this epsilon, the coefficient of restitution? Right. So this is related by. So epsilon is the relative velocity after separation, and this is after separation or after collision, right? And this is relative velocity before the collision. And as I have talked in the in the Newton's laws of motion, or what? I talked about this in the motion in 2D, right? I talked about the relative velocity. Right. So when this guy is moving with velocity VB and this guy is VA, so whenever two bodies are moving with some velocity, then we should always calculate what? The relative velocity. So let's say the train is moving in this direction and then this train is moving in this direction. So always calculate the relative velocity, right? Always keep in mind that whenever you see two guys are moving with two different velocity, then you always talk about the relative velocity, right? So as I was telling that the relative velocity after separation. So after separation, you had what? V1 and V2. So this would be V2 minus V1. Right. And let's just, so this is, I will say why I omit that vector part. And this is U1 minus U. So this is the coefficient of this restitution. Right. And if this guy is 1, then you have elastic collision. And if this guy is 0, then you have perfectly inelastic collision. And I will talk about this perfectly inelastic collision in a moment. And if you have E between 0 and 1, then this is called the inelastic collision. Right. Any doubt up to this point? I'm
No,
sorry,
sir.
guys. I'm sorry, guys. I am rushing. I'm rushing towards the syllabus, but what can I? I don't have a choice. Otherwise, we have discussed every part of our topic more significantly, but we don't have much time. I wanted to do problems also, but I have to finish this chapter today. Right. So what I was telling. Right. Yes. So Arpit, you see this diagram. These diagrams, and tell me, are these motion in 1D or 2D?
One dimensional.
Yes, so these are collision in one dimension. Collision in one dimension. Right. So I talked about the coefficient of restitution and the perfectly inelastic. And so these we are talking about in one dimension, right? So what is the concept of this elastic collision and this inelastic collision? So what are the physics that are involved in the elastic and the inelastic collision? Right. So in this, the linear momentum, the momentum is constant, right? We are not talking about the rotational part, so we are talking about the linear momentum. So momentum is constant, right? And for the case of inelastic collision, we have also momentum is constant, right? So momentum is constant. And in case of the other part is that kinetic energy is also constant. Right, and for this case, kinetic energy is not constant. Right. Okay, Sana. And why this happened? Because you have some conservative, so this conservative, and in this you have some kinetic energy is what? Some factor. So you have dissipative energy. So kinetic energy is what? So dissipated by some heat or by some other factor, right? So this is the conceptual part of the elastic collision and the inelastic collision. So let me for one dimensional, let me calculate. So elastic collision. Right. Let's say in 1D. So you have what this guy with u1 velocity comes and it has mass m, right? And u2 guy with u2 velocity and m2, and they collide and they move out. So this is what v1, m1, and this is m2, right? So first property of the elastic collision. And what was that? Sania, what was the first property of the elastic collision? Hmm? Okay. So Iram, what was the first property of the elastic collision? Okay, so then Anna, what is the first property of the elastic collision? Only Arpit and Marita answer. Why don't you
Momentum
guys?
is constant.
Yes, right. So yes, momentum is conserved, right? So momentum is conserved. So we will use this. Momentum is conserved, right? So let's say what will be the mathematical form when I say momentum is conserved. So this guy has momentum, and remember that we are in the one-dimensional motion. So we don't bother about the vectors, right? So this guy has velocity m1 u1, and this guy has velocity m2 u2. Right. So this is the initial momentum, and this will be final momentum. So final momentum will be what? m1 v1 plus m2 v2. Right, guys? So let's take care of this m1 guy and m2 guy. So keep m1 guy in this left hand side and m2 guy in the other side. So m2 v2 minus m2 v2. Right. So this becomes m1 u1 minus v1, and this becomes m2 v2 minus v. Right, guys. So let's say this is equation. Now we have utilized the first property. So can anyone help me and saying the second property? So what was the second property of the elastic collision? Anyone? Right, Samira. Yes, yes. So now everyone is. So kinetic energy is conserved. Right. Is conserved. Right, guys. So so this was what? So for first guy, the kinetic energy will be what? This half mass into velocity square. And for the second guy, we will have half mass into velocity square. And then for the final one, we have half mass 1 with velocity square and half mass velocity 2 square, right? So this will be what? So half cancel, right? Again, we will do what? We will take care of this same guy here. So we have m1 u1 square minus of m1 v1 square is equals to m2 v2 square minus of m2 u2 square. Right. So m1 u1 square minus v1 square, and this is m2, so v2 square minus v2 square. Right. So this will become what? So let's say this is equation second. And what we will do is that we will divide the second equation with the first one. Right. So dividing, we will get what? So u1 square minus v1 square by m1 and m1 u1 square minus v1. Right, and this m2 will be v2 square minus v2 square by m2 v2 minus v2. Right, guys, so this guy cancels, and this is a square minus p square, so we'll get u plus v1 and u minus v1. This will become u1 minus v1. And this is the same, so v2 minus u1, u2. And this is how much? V2 plus v2. So v2 minus v2. So this guy cancels, this guy cancels. So we are left with what? So we are left with u1 plus v1 is equals to v2 plus v2. Right. So in the collision part, what they usually ask, that they ask about the final velocities after the collision. Right, final velocities after the collision. So whatever we are doing, we have to find v1 and v2. This is RA. Right. In all those questions, they will ask only about these two, v1 and v2. Right. So let's calculate v1 from here, or let's calculate v2 first. So v2 is what? u1 v1 so u1 v1 minus u2. Right. So this is v2, and then we will put this value in equation first. So what was the equation first? This was the equation first. Let me write. Yeah, okay. Let me. Okay, so right, so we will put the value of v2 in here. So what will be v2? So m1 u1 minus of m1 v1 is m2, and v2 is what? u1 plus v1 minus u2 minus u2. Right, so this will become m1 u1 minus m1 v1 is m2 u1 and m2 v1. And remember, what is our goal? We have to find v1 and v2. Right. So m2 u1, m2 v1, and then minus 2 m2 u2. Right, guys. So we will keep this guy or this guy. So we will take this guy in here. So this will become m1 u1 minus m2 u1 and plus 2 m2 u2 equals to m2 v1. Let's say direct. I can write directly. So v1 m1 plus m. Right. So this will become what? u1 minus m1 minus m2 plus 2 m1 m2 u2 and v1 is this. So your v1 will be what? u1 m1 minus m2 by m1 plus m2 and plus 2 m2 u2 by what? m1 plus m2. Right. So you say if you have, we considered that both the masses were moving. Right. This we considered. So let's say if this was stationary, so u2 was 0. So v1 would have been u1 minus m1 minus m2 and m1 plus. Right. So this would have been your v1. So this is the general formula, right, for v1, and you can calculate for v2 also. Okay. And in this general formula, there will be some cases. Let's say your masses will be equal. So if your masses are equal, then this would be 0. V1 would be 0. Right. So this is about the elastic collision in 1D. Right. So for the inelastic collision, I have only 2 minutes. So I will just say for inelastic collision. And what is a perfectly inelastic collision? Perfectly inelastic collision. So the physical representation is this, that this guy was moving with velocity u1, mass m1, and this guy was moving with velocity u2, mass m2. They collide and they move together with some velocity v. Right. So this is the example of perfectly inelastic collision. Right, guys? So you can, if this is the inelastic collision, so you can calculate what? You can apply the first conservation, that is momentum will be conserved, right? So if your momentum is conserved, then what would be the case? Your m1 u1 plus m2 u2 would be what? m1 plus m2 into me. Right. So your v will be what? m1 u1 plus m2 u2 by m1 plus m2. So this is the velocity for the inelastic collision. And then what will be the kinetic energy? So the change in kinetic energy, delta K will be some value, right? This will not be, let's say, so yes. So your K initial will not be equal to the final, and there will be some change in kinetic energy, right? So you guys can calculate that. And what will be the change in kinetic energy? Half mv square minus half of m1. So this is change in kinetic energy will be what? Half of m1 plus m2 v square minus of half m1 u1 square minus half you calculate, that will be your delta P. So in a perfectly inelastic collision, in the question they ask you about the change in kinetic energy. So just remember that, right? And if you have the elastic collision, then you don't need to bother about this change in kinetic energy, right? Okay, so let me do one more conceptual part, and that is the elastic collision in 2D, right? So what does happen that if this guy comes and strike this second guy, right? Then they goes like this. So let's say theta 1. So this is V1 and M1. And this is the other guy, M2, which is going with V2. Right, so this is theta 2. Okay. So just remember that for this, so you can see that this is in the two-dimensional motion, right? So this will have, this theta will have, this momentum will have this what? Horizontal part, which is P cos theta, and this will have this vertical part, which will have P sin 1. Similarly, for this case, you will have P, well, let's say 1, 1. And P2 x, which will be what? P2 cos theta 2, and this will be the vertical part, P2 sin theta. Right. So in this case, always remember that for this elastic collision, your theta 1 plus theta 2 is 92. Just remember that. Right. And you have to apply the vector form. Vector form of the conservation of momentum and energy. Right. So what will be the vector form? So the vector form will be P1 plus P2 will be P3 plus P2. Right. Yes. So for elastic collision, what will not happen? For elastic collision, the theta 1 plus theta 2 will be 90 degrees. Right. So when you use the momentum conservation, and okay, so you're asking what will happen if your theta 1 plus theta 2. So you can see.
No, sir, I was just asking.
Yes. So if you say that your theta 1, let's say in your question, they ask that your theta 1 plus theta 2 is 90 degrees. So you can directly say that the collision is what?
Elastic. Okay.
Yes,
sir.
yes. So yes. So if they give you that your theta 1 and theta 2 is 90 degree plus, then this collision was elastic collision. So the other way to see is that if you apply this, I don't have time. Otherwise, I would have shown that theta 1 plus theta 2 will be 90 degrees.
No,
So
sir, it's fine.
So if P and Ke conservation is applied, so you can see that with the help of these two conservation, you can reach here, right? Right.
Yes,
So this,
sir.
yes. So another part I was, yes. So half kinetic energy initial is kinetic energy final, right? So in vector form, this would be what? In vector form, half of m1 u1 dot u1 plus half of m u2 dot u2 will be equal to half of m1 v1 dot v1 sorry, yes, v1, and then half m2 v2 dot v2. So this is the form of the kinetic energy for the case of vector form, right? And we can also see that what will be the, so P1 will be what? Okay, sorry guys, I have taken your 7 minutes, so just giving me 2 minutes, right? So this will be what? P1x I hat plus P1 y j hat, right? And you guys already know what is P1x and P1y. So again, so P2 is what? P2x I hat plus P2yj. And when you compare with, so P1x I hat plus P1yj hat plus P2x I hat plus P2yj hat, which is equal to P3x I hat plus P3yj hat plus P4x I hat plus P4yj hat. Right. So when you compare I, so your P1x plus P2x will be equal to your P1 P3x plus P what? 4x, and your P1y plus P2y will be equal to P3y plus P4y. And you can already see from here that P1x will be P. Okay, so so this completes the concept of this work energy power, right? So yes. So guys, sorry about that. So this completes this chapter, right? And in the next class, I will do another chapter. Right, guys. So thank you guys for listening. I apologize that I rushed through these chapters because I have to complete all the other parts of which are remaining. Right, guys. So okay, guys. So let's meet on what Saturday, and then we'll discuss about kinetic theory of gases, our next chapter.